Hello again everyone, welcome back to ptet.chemistry channel. In this tutorial video, I'll go through this November 15, paper 1-2 for the Cambridge International A-Level curriculum. This is a set of multiple choice questions covering the advanced chemistry, which is the first year of the 16 to 18 years old chemistry curriculum. In this first question, which type of bonding is never ever found in elements? So we know that elements are stated in the periodic table. That's why it's called periodic table of the elements. Of course, we can have van der Waals forces between the molecules. So this could be between like H2, between F2, Cl2, O2, N2. But then we also have monoatomic noble gases like helium, neon, argon, etc. They also have van der Waals forces of attraction between the molecules, between the atoms in the case of noble gases, but between the molecules for these diatomic molecules. These are all elements as stated in the periodic table. You could of course have metallic bond as well. So metallic bonding you will have between all the group 1, group 2 metals. So your periodic table will probably show group 1, group 2 like that. And of course you also have transition metals, transition elements. They are all metals as well, so obviously they are metallic bonds. And of course we also have covalent bonds. So covalent bond is associated with this molecule here. So what I'll do is I'll just group these couple of elements together. So this thing exists as diatomic molecules. So this thing here will be your covalent bonds. I don't specify all of that elements stated there because these are noble gases, no covalent bonds. So it's just van der Waals forces of attraction there. Of course, we also get covalent bond when we have like diamond, graphite. So these are giant covalent structures. Among other elements, such as these simple molecules, all of them will have covalent bond. It's just that you also have van der Waals between the simple covalent molecule. What you don't have will be ionic, because when you have cations and also anions, so you must have different type of elements like that, because they are on different spectrum of the bonding kind of different spectrum of the electronegativity. That's why they will form cation and anions, and that's why you don't get ionic bonds between elements. Question 2 is about balancing equations. If I were you, I would try and balance it from scratch, I guess. What do I see? I see there are chlorine here, but there's chlorine there and chlorine there, so that's not going to be nice at all. But the arsenic is something I can relate to, so P must be equal to R. There's something I can relate to. P must be equal to R, P equal to R, P equal to R, P equal to R. So that one is okay because of balancing the arsenic. In terms of the sodium, hope you can see that Q must be equal to S. So look for Q equal to S. So let's choose a different color. Q and S are the same, Q and S are the same, Q and S are the same. So Q and S doesn't help me very much. How about the next one? Looking at the chlorine or looking at the hydrogen? I think looking at the hydrogen is a lot easier. If you see there are 4 hydrogen and there is Q there. So in terms of hydrogen atoms, there will be 4 times Q on the left hand side. On the right hand side, you have 3 times R hydrogens. So 4Q equal to 3R. Let's just have a quick look. 4 times 3, 4Q, 4 times 3 is 12. 3 times 2 is 6, so I know A is definitely wrong because of 4Q equal to 3R based on balancing equation then. Now this is 4Q, 4 times 3 is 12, 3 times 3 is 9, so again I can tell that that is wrong because of 4Q equal to 3R from our relationship. Having said that, we are left between C and D. So 4 times Q is 12, 3 times R is 12, that one is okay. 4 times Q is 4 times 4 is 16, 3 times 4 is 12, so the last one is wrong, which means C must be the only correct answer. But just because I say it's the correct answer, I might have made a mistake, so I'm going to put the number in front there, 43433. Let's just do a quick check. So in terms of the chlorine, 4 times 3 chlorine, 3 times 1 is 3 chlorine, 3 times 3 is 9, 3 plus 9 is 12 chlorine, that one's balanced. In terms of the hydrogen, 3 times 4 is 12, 4 times 3 is 12. That was how we managed to get the correct answer by eliminating the impossible options from this relationship 4Q equal to 3R in terms of the hydrogen atoms there. Question 3. These are structure and bonding and their properties. So what could be the identities of U, V, and W? When you look at the melting point of this last one here, this is negative. This is telling you that these are low melting point. These are relatively low boiling point as well. So I'm not saying it's very low, but it's relatively low boiling point. We can be thinking about this as a volatile, and therefore W must be simple molecular structure. Okay, simple molecular structure or simple covalent structure. What other information do we have? The poor electrical conductivity when solid liquids suggests that it cannot be ionic, which again, confirm that it's simple molecular. But the very last thing, hydrolysis. And then once it hydrolyzes, the resulting solution conducts very well. We know that C2H5Br does not hydrolyze easily. In fact, if you have learned organic chemistry, you will need aqueous NaOH and reflux for hydrolysis of these halogenoalkanes. Whereas when you have HCl dissolve in water, it doesn't hydrolyze like that, dissolve in water. Well, you can think of it as hydrolysis, I guess, because the HCl bond actually has to break in order to give you the H plus and Cl minus. So it could be HCl as well, to be honest. But SiCl4, as you know, definitely hydrolyzes. The silicon chlorine bonds get broken down. You get SiO2 white precipitate, which is insoluble in water. And these equations happen to be one of the very common one that asks you in structured question. Well, anyway, I know I can rule out B, and because of that C2H5Br, but I can't really rule out A, C, and D yet. Okay, let's have a look at element or substance U, because we are not sure this element, but of all these, the U there, they are all shown as metals, they're all shown as elements. We know that sodium can conduct, well, metals, sodium and zinc can conduct very well as solid and liquid because of your metallic bond, and that in the aqueous state they're insoluble. But what is important is this 420 and 907. We know that sodium being a group 1 metals, as you know from all level, GCSE and IGCSE level, they have very special kind of properties. Their melting point is relatively low compared to all the other metals. These are very high. In fact, the melting point of sodium is just below 100 degrees Celsius, so it can't be sodium there. So A is out of the option as well. So we know it can be zinc there. Looking at V, we have poor electrical conductivity when solid, but good when it is liquid, suggests this ionic compound. Both of these are ionic compound. In terms of the melting point, I don't know how I'm going to decide on the melting point. I guess both of them will have very high melting point as ionic compound, which conduct even when aqueous solutions. All potassium and all sodium salts are soluble in water. So I guess it really comes down to the HCl and SiCl4. The fact that we talk about hydrolysis there, we don't typically talk about hydrolysis of HCl, but we talk about hydrolysis of SiCl4. So I think our best answer there has to be option D and not option C there. Question 4 is about your ideal gas equation, but not really the whole ideal gas. This really comes down to volume. So this is the volume of gas. This is the pressure of gas. This is simply one part of the ideal gas. It's actually Boyle's law, PV equal to constant. So this is at constant temperature, which is why the Boyle's law definition is not complete unless you say at constant temperature there. You have learned that pressure of a gas is inversely proportional to the volume of gas at constant temperature, such that PV equal to constant. If PV equal to constant, so previously you have these two, they are disconnected, and now you connect them together. So my P1, my V1 is that, my P1 is that, my V2 is that, my P2 is that. And now my final pressure, so this is the total pressure, is what I want to find, and my total volume is going to be the sum of the volume of the gases, so 5 plus 10 is 15 dm cubed. This is my V total. So what I can get is P1 V1 plus P2 V2, each one is a constant on its own, and then this is equal to P total, V total, another constant. So based on that formula alone, I can get 12 kilopascal times 5 dm cubed plus 6 kilopascal times 10 dm cubed equal to my P total is what I want to find, and then my V total is 15 dm cubed. So I'll keep all the volume as dm cubed, I'll keep all the pressure as kilopascal, and that's why my P total will be in kilopascal. So press your calculator. My P total will be something divided by 15. On the left hand side, 12 times 5 plus 6 times 10, I get 120. So 120 divided by 15, I get 8. This thing has a unit, kilopascal there. So A is the only correct answer. So question 5. Calcium forms an ionic compound with carbon called calcium carbide. The oxidation number of carbon in calcium carbide is -1. So it's carbon -1 in calcium carbide. When you hydrolyze calcium carbide, so you can break the bond there, in the presence of water, you get 2 products. What would be the formula of calcium carbide? If we work out the oxidation number, we know that calcium as a group 2 element in a compound is exclusively calcium plus 2 when you form compound. So if I work out Ca2C, the compound has a 0 oxidation number. I have 2 calcium, each calcium is plus 2. The carbon there is going to be -4, which means it is not -1, which means A and B cannot be the answer, which means C and D must be the correct answer. I could show it to you. Calcium carbide, if it is CaC2, 0 is the overall oxidation number of the compound. Calcium is plus 2, I have 1 of it. I have 2 carbon there, so 2 carbon equal to -2. Each carbon is -2 divided by 2 is -1. As stated in the questions, oxidation number of carbons in the calcium carbide is -1 there. In terms of the products, we need to think about the hydrolysis. So calcium carbide, CaC2, plus H2O, we need to try and balance the equations. You will never ever get calcium oxide on its own, because calcium oxide can dissolve in water to give you calcium hydroxide. So I think C must be wrong, but let's just write an equation for the second one, for option D, and see whether we can convince ourselves that is the answer there. So 2 carbons, H4 plus 2 hydrogen is H6, so I need 6 hydrogens, therefore I will have 3 H2O. And that doesn't seem alright, so perhaps I was wrong. We need to try and balance our equation, right? So I wonder if I have done something wrong. H4, H6, would that be balanced? Perhaps if I have calcium oxide, would that be balanced instead? Let's see, calcium oxide plus C2H4. So 4 hydrogen, 2 there, O2, if I have 2 there, that is not going to balance as well. So I don't know. I don't think you get calcium oxide on its own, because we are talking about in the presence of water. You know about when you spread calcium oxide on soil, they can react with the water, and they will in fact not stop at calcium oxide. They will just give you the solutions of the calcium hydroxide. So I still stand in my belief that D is definitely the best answer given the circumstances here. Question 6 is about the use of Hess law. So Hess law says that the enthalpy change of a reaction is independent. It does not depend on which path you take. So W is going from reactant to product directly. You could take the indirect path as long as you start from the same reactant and end up the same products. It doesn't matter which path you take, the enthalpy change is going to be the same there. So W is the direct route, U is the indirect route, but U has to go opposite to V, so it has to be U minus V there. So what do we get? U is the sum of the average bond energies, and V is the sum of the average bond energy of the products. So this is using bond energy. We know the enthalpy change of a reaction when you have bond energy is the sum of the bond dissociation energy, broken minus formed. Broken minus the sum of the bond dissociation energy for everything that you are forming. So I've talked about broken there, but that is essentially the bond dissociation energy of the reactants. Basically what you need to break, and that is the sum of the bond dissociation energy for whatever you need to form, which is the product side. So there is the broken minus the formed thing, that is the bond dissociation energy of the reactants minus the bond dissociation energy of the products there. So in terms of what we have here, which expression will give a value for W? W is the enthalpy change for this reaction. So U is the sum of the bond average bond energy of the reactants. So what we're going to get will be carbon gas, and then we get 4 hydrogen gaseous atom. We also get 4 oxygen gaseous atom. So this is forming. This is forming the gaseous atoms. So that is essentially breaking everything in the reactant site. That is going to be U there. So that is just U, which is the sum already. And then that thing there is going to be V there. So that is already the sum there. So W must be equal to U minus V, just like that. So it has to be option A as the only possible answer there. Question 7. So this one has been taken out from the current new syllabus because this is electrolysis of aluminum oxide with cryolite. I think at the moment the new A-level curriculum, they just focus on the disproportionation, the oxidation number, without the case studies on the electrolysis that you have done from O-level, GCSE level or IGCSE level. Regardless, I'm just going to go through this anyway. What are the reactions at the anode? We know that anode attract anions. So anode attract anions. Anions are going to be negatively charged, so anode is positively charged. So what happened at the anode is going to be the opposite of what happened at the cathode. Red cat means reduction at the cathode, and we know that reduction is gain of electron from that RIC acronym there. So reduction is gain of electrons, which means that we have oxidation at the anode, and oxidation is going to be loss of electrons. And you are going to lose electrons at the anode. So this is gaining electrons. I know A and B are out. In terms of losing electron, this is losing electrons. So this one is, hang on, no. This one is losing electrons, so this one is okay. Anode for each of these process. So this one is also losing electron, this one is okay. But we got to think about the two different case studies. The purification of copper. So you're transferring the copper from the impure anode to the pure cathode. So this is something you have done in your previous study on electrolysis. So from the impure anode to the pure copper cathode there. So at the anode, your copper will dissolve away to give you the copper 2+. They get transferred to the cathode and they will get deposited as the pure copper. For the extraction of aluminium, all you have is your Al3+, O2-. So O2- is in your electrolyte and not OH- because Al2O3 is actually insoluble in water, and that is the very reason why we have to melt it at a very high temperature, and we use cryolite to help decrease the very high melting point there. Question 8 is to do with a Lee-Chatelier principle. So we know Lee-Chatelier principle helps to guide you on the position shift in the equilibrium. You want the greatest equilibrium yield of hydrogen. Hydrogen is on the right hand side, so you want to favor the right hand side. The first thing you notice is the forward reaction is endothermic. So if the forward reaction is endothermic, that means the forward reaction absorbs heat. So what happens when we increase temperature? So that means the system or the reaction, they want to decrease the temperature. They want to lower temperature. So what happens when they want to lower temperature? The system will absorb more heat. By absorbing more heat, you will remove the heat that you supply in the sense that you're increasing temperature, you're supplying heat. So to lower the temperature, your system will do the opposite to counteract the thing there. They'll absorb more heat because that's all it knows what to do, is endothermic. When you absorb more heat, you're going to favor the right hand side because the reactants absorb heat to form the products. As you absorb more heat, you will favor the right hand side. Okay, so equilibrium shift to the right. If your equilibrium shift to the right, you will get higher yield of your hydrogen. So to get the higher yield of the hydrogen, we definitely need high temperature and not low temperature. So B and D are out. In terms of the pressure, we always look at the mole of the gases. So focus on the stat symbols. We have 1 mole and 1 mole. So we have 2 moles of gases on the left. And then we look on the right hand side. We have 1 mole of CO and 3 mole of H2 gas. We have 4 moles of gases on the right hand side and 2 moles of gas on the left hand side. So the more moles of gas means you have more gaseous molecules. More gaseous molecules that will collide with the wall, and therefore this side will have greater pressure on the walls of the container. When you increase pressure, your system wants to decrease pressure, so it will shift to the side with lesser gaseous molecule. So increasing pressure will make the equilibrium shift to the left hand side. You will get lesser H2. So to get more H2, you want to shift to the side with more gaseous molecule. You want to try and increase the pressure, and you want this one to move to the side with more gaseous molecule. So you have to do the opposite. You have to lower the pressure. So when you lower the pressure, the system, the equilibrium will want to increase the pressure. It will want to shift to the side with more gaseous molecule there. Question 9, this is just numerical calculations. These are already partial pressures. Because these are already given as partial pressure, your life is quite easy here. So Kp is in terms of partial pressure. The products on the right hand side expresses the partial pressure, and it's a square because you got a 2 in front of the balance equation. This is divided by PNO square because the NO is a reactant. It appears at the bottom of the Kp. It's got a square because it's got 2 in front of the equation there. And this is the power 1 because it's just 1 in front of the O2. Now you just want the Kp. So what we do is we just put in the value. The NO2 partial pressure is 20 square like that. And then at the bottom I have 10 square, and then I have 30. Okay. So pop that into your calculator. 20 square divided by 10 square divided by 30. I get 0.133. So if you look at the scientific form, that is going to be 1.33 times 10 to the minus 1, as I could move my decimal place like that to the right hand side. It will give me a minus 1 there. It has a unit, so these are kilopascal. So this thing here, the unit will be kilopascal square over kilopascal square times kilopascal. The square and the square cancel. I get kilopascal minus 1. If this is a structured question, you'll probably get 1 mark for the unit itself. Question 10. This is a decomposition reaction. You have a reaction pathway diagram. This is your reactant. This is your product. From your reactant to the top of the peak, X is going to be activation energy. But you also have this thing here. The Y is going from the product side to the top of the peak. This is also activation energy, but for the backward reaction. Okay, so you're going backward from the product to the reactant side. This is from where you start to the top of the peak. This is where you start from the reactant to the product. This is EA for the forward reaction. In terms of the enthalpy changes, enthalpy change is from the start to the end. From where you start to the end, so that is actually the enthalpy change of the forward reaction. In terms of the backward reaction means you go from the products to the reactant. So I'm going to start off from the products to the reactants, so where you start to the end. So that green color there is your enthalpy change of a backward reaction. So what is the question actually asking? What are the values of the enthalpy change for these reactions? They did not mention that this one is a reversible reaction. So they're just going from the reactant on the left-hand side to the product on the right-hand side. So enthalpy change is actually referring to these from the start to the end there. They are referring to this blue colored thing here instead of the green colored thing. The enthalpy change of the forward reaction there is going to be a positive value. It's going to be X minus Y. X minus Y is going to give you a positive value. This is bigger than that. It will give you a positive value corresponding to the enthalpy change of the forward reaction. X minus Y is correct. And then the activation energy for this reaction from the start to the top of the peak is just X there. Okay, hopefully you can read that carefully. Question 11. What happened when the temperature of a chemical reaction is decreased? So this is about your Boltzmann distribution diagram. We have energy on the x-axis. We have number of molecules with energy E on the y-axis. If I just draw a Boltzmann distribution at one particular temperature, and then I draw another Boltzmann distribution at a higher temperature. So this thing here, I will just label as the activation energy of a reaction. So when I go to the blue color line, that is at a higher temperature, which means I want at a lower temperature. So I will go the opposite way, which is going this way. So that will be lower temperature. Temperature is decreased. So in terms of the activation energy, they will remain the same. They don't change at all. You are not using a catalyst. In terms of the number of successful collisions, also known as effective collisions, so we look at the area under the graph with energy greater than or equal to EA, which of course when you shift to the left-hand side, when you shift to the green color thing there, so your green color is just that area under the graph. But when you shift to higher temperature, you also have the additional blue color region plus the one underneath it. So you will increase the proportion of effective collision as you go to higher temperature, but when you go to lower temperature, you will decrease the proportion of effective collision because the area under the graph represents the number of molecules, the number of reacting particles with energy greater than or equal to EA has decreased when you lower the temperature. So the number of successful collisions will have decreased, giving you C as the only possible answer.